I would like to introduce our speakers today. Dr. Dai Wang is a senior bridge engineer and steel specialist for the FHWA Office of Bridges and Structures, responsible for steel bridge-related technical issues and programs. He received his doctorate at Lehigh University, and he has over 25 years of experience as a consulting engineer and fellow at HNTB in Jacobs. He joined FHWA in 2016. Jamie Ferris is the Deputy Director of the Bridge Division at Texas Department of Transportation. In her role, she assists in overseeing operations that include planning assistance, geotechnical and structural plan preparation, construction and maintenance assistance, safety inspection, and TS&E review. Ms. Ferris graduated from the University of Texas at Austin with a BS in architectural engineering and an MS in civil engineering with an emphasis in structures. She joined Texas DOT in 2003 after spending 3 years in the consulting world. Andrew Smith is a bridge load rating engineer with the Wisconsin Department of Transportation Bureau of Structures. He specializes in refined analysis methods for load rating and permitting some of Wisconsin's more complex bridges. Over the past few years, he's been actively involved in efforts to load rate for special haul vehicles and more recently, emergency vehicles. He is also involved in the repair and strengthening of bridges related to bridge hits, structural deterioration, and load posting avoidance efforts. He joined WISDOT in 2010 after graduating from Marquette University with both a BS and MS in civil engineering. And Dr. Wang will be our first speaker today. So Dai, thank you for being here, and I'll let you take it from here.
Thank you, Nate. To start with the webinar, I'm going to briefly talk about fracture control in steel bridges, focusing on system redundant member provisions, SRM. My talk will be based on provisions defined in the current version of CFR and NBIS, which are the legal base of FHWA position on this issue and are the operation practice by Federal Highway Office of Bridge and Structures. In the past half a century, we had fracture-induced failures in steel bridges, which made fracture control necessary. Among the fracture-induced failures, there was the well-known Point Pleasant Bridge collapse in 1967, causing 46 lives. This old 1928 bridge collapsed due to brittle fracture of an I-bar with marginal fracture toughness of heat-treated steel and flaw that may have been caused by stress corrosion and fatigue. The fracture of low toughness material through an inaccessible detail led to the bridge collapse. This catastrophic failure led to the development of fracture critical member provisions, the 1978 guide specification for FCM, and the NBIS, National Bridge Inspection Standards. Another fracture-induced failure was the Minas River Bridge collapse in 1983. The two-girder bridge collapsed due to failure of the pin and hanger system in a suspended span. Since then, NBIS added the provision of hands-on inspection. Home bridge failure was another typical case. All three girders were found fractured due to constraint-induced fracture details. The fracture failure happened without warning, without the indication of fatigue crack growth. The failure happened at a highly constrained detail with high tensile stress and a crack-like condition. There are a number of other fracture failure caused cases in steel bridges. Fracture control is really necessary. The current fracture control practice in the US for steel bridges includes fabrication FCP, fracture control plan, with higher standard of steel toughness and fine grain, and also higher standard of shop fabrication, welding, and inspection. The first version of FCP is the 1978 AASHTO non-redundant FCM guide specifications, and the most current version is the AWS C15 Class 12. The second leg is the in-service inspection, in-depth and a more frequent hands-on FCM inspection and a 2-year interval. This is per National Bridge Inspection Standard, NBIS. Beyond this 1 and 2, there is a design more beyond those two. Contingency, continuity, and composite. For example, for I-bar suspended span like a Minas River Bridge, in addition to more in-depth inspection, many efforts were made to make the span continuous or to add catch-up system at I-bar locations. Make details accessible. For example, we have no new design using important details inaccessible to inspection, like the Point Pleasant Bridge. In fact, the sister bridge of the Point Pleasant Bridge was quickly dismantled as there is no way to detect similar problems. Also, avoid constraint-induced fracture details in new design. The CIF problem needs to be addressed more than FCP and inspection. Please remember, all these practices are in compliance with the current CFR and NBIS. In fact, since 1978, our fracture control has been quite successful. After the FCP in place, we haven't seen fracture-induced bridge collapse. We'll keep this good fracture control practice as our valuable assets in our toolbox. But the question is, this fracture control practice costs more, sometimes costs much more. We need to apply FCP only as necessary, especially on item 2, FCM inspection. Fracture control is only needed for fracture critical members. For current CFR and NBIS, FCM is defined as a steel member in tension or with a tension element whose failure would probably cause a portion of or the entire bridge to collapse. Please pay attention to the two keywords, failure, collapse. No collapse, then not FCM. Federal Highway 2012 FCM memo allowed system redundant member with this definition: a non-load path redundant member that gains its redundancy by system behavior. SRM is considered to give a relief of unnecessary requirements for FCM. Do we need to talk about the system redundancy of a full girder bridge? No. The bridge has load path redundancy, so don't waste your time here. Per Federal Highway 2012 FCM memo, SRMs are not FCMs, do not need FCM inspection, as the failure would not cause the bridge to collapse. Also put that memo, to demonstrate SRMs, a state must submit through the division office of FHWA with the detailed analysis and the evaluation criteria. Once reviewed, these criteria can be employed by the state systematically on their inventory. I want to mention, if using today's good guidance language, This memo could have been used the term of should instead of must. However, there's no change of the clearly defined process. For a type of members without a load path redundancy, the SRM determination should follow an FHWA accepted procedure, which may be done in several possible ways, either through analysis or without analysis by satisfying a list of conditions or by comparison with previously determined SRM. I want to mention the procedures acceptable to FHWA. Those include AASHTO SRM guide specifications, which is acceptable to FHWA. This procedure requires forensic refined analysis, or called a full 3D nonlinear dynamic finite element analysis, with techniques beyond everyday dynamic everyday engineering analysis, such as modeling friction and individual shear studs there. This has been successfully applied at the Wisconsin DOT FC analysis phase 1 and 2 twin top girder SRMs accepted by FHWA. Later on, Andrew will elaborate the details of the results. Procedures based on experimental and analytical research and accepted by FHWA as a second type. This kind of procedure uses linear elastic engineering analysis. The examples: TxDOT, engineering criterion, and the procedure for the evaluation of system redundancy in steel twin top girder bridges. The procedure was accepted by Federal Highway in November last year. Later, Jamie will present the procedure and the results. Another example, Purdue University, AASHTO twin top simplified SRM procedures draft, proposed to AASHTO T14 in December last year. Last week, we saw a modified version. The final may be accepted by FHWA once finalized and submitted. Let me clarify the concept here. Accept does not mean requiring everyone to use the procedure, nor to require all its details. Second, good engineering still must be exercised. It's worth to mention that SRMs in major projects may be handled individually through refined analysis with bridge-specific criteria. FHWA has done in the past on Tennessee Bridge, the Goldie Hall International Bridge, and the East End Crossing. Next, let's welcome Jamie of TxDOT to present and share their procedure and experience. Jamie?
All right, thank you, Dai. Thank you, everyone, for joining us today. Thank you also to AISC and NSBA for allowing me to share TxDOT's experience and with gaining approval for deeming newly designed steel twin tub girder bridges to be system redundant. So let's get started. So today I'm going to talk to you a little bit about the background for our twin tub girders in Texas, research that was done, designing for redundancy. We're going to look at our Texas SRM design methodology that was just mentioned. I'll take you through kind of what we went through for FHWA approval, and then I'll talk about what we're going to do to move forward. So today my presentation is about steel twin tub girders, which consist of two steel box girders that have a composite, that are composite with a concrete deck. The bottom flanges and webs are considered fracture critical in the positive moment region, and that because of that, they require hands-on inspection every 2 years. Steel twin tub girders are effective for curved ramps and connectors and multi-level interchangers, as shown in this picture. And this picture is taken from Google Earth, and it's in Austin, Texas, at IH-35 and US 290. So out of all the fracture critical classified bridges in Texas, the steel twin tub girder bridge is one of the most common ones. Texas has over 480 existing twin tub girder spans, and we spend about $2.3 million every 2 years on inspection of these bridges. And I do want to point out that that figure doesn't include the costly traffic control that goes into inspecting these bridges. So now I'm going to move into the research part. So in around 2010, a research report was published at the University of Texas at Austin. And this is a TxDOT research project looking at the modeling and response of fracture critical steel box girder bridges. This was a huge research project, and I have 9-5498, but there was several different numbers, I guess, involved, but that 5498 is going to be the main number that you would search for to look for any documents pertaining to this research. And so this research characterized the redundancy that exists between twin tub girder bridges. They developed guidelines for modeling behavior in the event of a fracture of the tension flange and the web in tension. And the research included laboratory testing, full-scale tests of a twin tub girder bridge, and then detailed structural analysis. So this bridge was taken out of service in Houston, and it was hauled to the Ferguson Laboratory in Austin, Texas. And so this is the bridge that used for their full-scale testing, and they tried to mimic TxDOT construction practices when they built a slab and added the rail. It represented the worst case, so it was simply supported. There were no external intermediate diaphragms. The bridge rails had expansion joints, and this bridge was also horizontally curved. So now I'm going to take you through, just briefly through the test. You could do a whole presentation just on the research. So this is going to be just kind of a really quick snapshot. So for the first test, the researchers simulated a fracture of the bottom flange using a linear shaped charge explosive. And so this rapidly cut the bottom flange. And then they had an equivalent of an HS-20 truck positioned directly above the fracture at the most severe location. They did a combination of analytical and full-scale testing on the specimen. And the bridge performed very well. It only deflected less than 1 inch. So for the second test, the bridge was raised back to its original elevation before the first test using scissor jacks. The web was then cut on that same outside girder that the flange was cut. And so this provided a full depth fracture. The loads were induced and applied suddenly by explosive acting on those that temporary support system. And so same thing as the first test. The bridge performed well. The fracture girder only deflected by 7 inches. And so even in its damaged state, this bridge could support traffic and it did not collapse. So the third and final test was conducted under statically applied loads, and the bridge was able to carry 363,000 pounds. So that's more than 4 times a legal truckload. And so again, this bridge demonstrated, that it is system redundant. And I also want to point out that kind of like what I said before, this bridge was taken out of service. So it was an older bridge. It definitely wasn't designed for system redundancy, but yet it demonstrated system redundancy. The research highlighted the importance of the deck and the shear connectors and their contribution to the system performance. And then also they observed that the barrier railing contributed structurally. So now I want to talk a little bit about designing for redundancy. So I'm not going to go into great detail because Dai just talked about this, but so you had 2010, the research report was published, that research was finished. And then if you go through time, 2012 comes along and FHWA publishes a memo and where they introduce a new classification for SRM. And so, you know, kind of like what we talked about earlier, this provides a path to design new steel twin tub girder spans that can be shown to possess adequate redundancy such that the bridge will not collapse. So, you know, this kind of got TxDOT thinking, you know, what if we can design new twin tub girder bridges to be system redundant? And this would eliminate the requirement for the hands-on inspection every 2 years for the life of the structure. And as you know, these inspections often take place at night on direct connectors with a high volume of traffic. And also traffic control is costly and could be unsafe for the traveling public because it's a change in traffic patterns. So after that 2012 memo, TxDOT met with FHWA to discuss how we should move forward. And the starting point that was proposed was to use the analytical modeling methods from that 5498 research project. And so that research project, there was a simplified method that was developed, and it assumes a full depth fracture of one of the girders. And so TxDOT bridge engineers analyzed 3 example existing steel twin tub girder bridges using that simplified procedure. So the 3 case studies represented a typical flyover steel twin tub bridge found in Texas. And so, for example, this was one of the bridges, existing bridges that was a case study. And it was a direct connector in Austin, Texas, on US 290 and IH 35. So the results of the redundancy case study indicated that the intact girders had sufficient bending capacity as well as adequate deck shear strength and shear stud tensile capacity. But in all cases, the intact girder failed and combined torsion and shear at the supports, but that margin of inadequacy was small. And so below just shows just kind of a chart of the geometry of each of the case studies, the year it was built, so that you can get an idea of exactly what we looked at. So compared to that 5498 experimental bridge, which had a span length of 120 feet, the 3 case studies had longer span lengths. They had a sharper horizontal curvature, which led to a greater dead load, a larger eccentricity, and therefore a higher torsion and shear at the support location. So all 3 cases didn't pass that simplified method criteria. And that was just at the support girder section shear capacity check due to that torque and shear forces. But none of the cases failed due to lack of shear stud tensile capacity. And so this led TxDOT to believe that new steel twin tub girder bridges could be designed and detailed for system redundancy so that they wouldn't be considered fracture critical and safely carry live load without collapsing. So that brings us to 2016. In 2016, TxDOT instituted a twin tub task group. The task group membership reflected the overall structure of the Texas Steel Quality Council, with 17 members participating. So if you don't know, the Texas Steel Quality Council, it was originally established in 1995. It's a joint owner industry forum. It's made up of TxDOT inspectors, designers, fabricators, erection engineers, consultant engineers, FHWA, academics, detailers, trade association representatives, steel mill representatives. So basically, anyone in Texas involved in steel or steel bridges. And the goal of the task group was to develop LRFD-based design specifications that would govern the analysis and design of non-fracture critical steel twin tubs. So an AASHTO ballot item was developed and presented at several industry and AASHTO meetings. But in the end, AASHTO was not ready to put the language in the specifications just specifically for twin tub girder bridges. So at that point, TxDOT was encouraged by FHWA to submit for approval as a state. And so this was very encouraging because, as you can see, TxDOT had spent a lot of time and effort for this bridge type. And so we definitely wanted to take this forward, take it to the finish line. And so this led TxDOT to develop language for its own bridge design policy. And so I'm going to talk about that next. So in 2020, earlier this year, we published a new revised bridge design manual. And within that manual, we present a methodology where you can design spans or twin tub girder spans so that they will not collapse after you fracture one of the girders. So to complete this design methodology, number one, you would first just design your bridge like you normally would, using a couple of limit state, couple of exceptions. So you would design for your strength limit state using a redundancy factor of 1.05. You design for service limit state, and then you would design for infinite fatigue life for that fatigue and fracture limit state. And then the next step, you would design your bridge for member failure. I'm going to talk a little bit about that. So now I want to just kind of talk about how you would determine which girder to fracture and where to fracture the girder using the TxDOT method. So the bottom flange and tension and the webs attached to that flange of the critical girder are assumed to be fully fractured at the location of the max factor tensile stress in the bottom flange determined using the strength 1 load combination. To result in the worst case loading scenario, the assumed fractured girder is chosen based on its position in the cross section relative to the traffic lanes and its eccentricity to the deck and railing. The methodology also points the designer to check simple spans and end spans of continuous units to be the most conservative. If a span is horizontally curved, the girder with the largest radius is assumed to be the fractured girder. So the decision to use the probability of such a fracture for tub girders designed for infinite fatigue life is considered exceedingly small in comparison to the bridge's design life. So the TxDOT method addresses the design of a simulated fracture with the extreme event limit state. TxDOT revised the AASHTO definition of the extreme event limit state to include the structural member or component failure. And what I was about to say was this decision to use the extreme event was also based on precedents that have previously been set. So for example, the alternate path analysis and design guidelines for progressive collapse, which is published by the General Services Administration for buildings, uses an extreme event. The FHWA guidelines for cable stayed and arch bridges uses an extreme event. The Pennsylvania DOT design manual uses an extreme event for the failure of a component without the collapse of the structure, and that has been in their manual since the mid-90s, we've been told. So this just kind of gives you a look at how we address this, and that's, we revised the table to show an extreme event 3, and this would be for components, or this would be for that system redundancy for the twin tub girders. And so basically we would supplement AASHTO tables in Chapter 3. And then all the load effects assumed in the fracture event are amplified by a factor of 1.2. And this is to simulate the dynamic effects of a fracture on the twin tub girder spans. And this shows in blue, the blue box just shows a summary of that extreme event load combination. So a little bit about live load. The live load for this design methodology includes both the truck and the lane. So that truck is positioned on the bridge directly above the proposed fracture location. And this is just to get the worst effect. The number and the width of design lanes equals the actual number and width of the striped lanes on the bridge. The design engineer must also provide internal and external diaphragms at all supports. The diaphragms and connections must be designed to resist the torsional moment and the assumed intact girder. They also must be designed to transmit vertical and lateral forces to the bearings during and after the assumed fracture event. And they also need to be designed to act compositely with the slab with the shear connectors. So at least 2 permanent external and intermediate diaphragms must be provided at each side of the location of that max factored tensile stress in the bottom flange. And those intermediate diaphragms, you know, they should be at a certain distance, and we give that distance in our manual. And this is just to enhance system redundancy by providing additional load paths on each side of that assumed fracture location. So you also need to check the intact girder and portions of the fractured girder that can still resist load for adequate flexural and shear resistance after the assumed fracture event. For both of these, you would use the extreme event 3 load combination according to the provisions of AASHTO. And I have here the AASHTO articles that you would use for flexural resistance and the positive and negative flexure, and then also for shear resistance. So next, you also want to check for shear for the concrete deck, the end diaphragm, the shear connectors, and the top flange lateral bracing. So for the concrete deck, you need to check adequate shear resistance to resist shear due to torsion after the assumed fracture event. You would use extreme event 3, and you would use the provisions according to Article 5.7.33. And then also, if you want to use the TxDOT design methodology, the empirical deck design is not allowed. You also want to check the end diaphragms and their connection to both the tub girders, to both of those tub girders, just to ensure adequate shear resistance to the torque applied to the intact girder after the fracture event. And then you would also use extreme event 3 load combination. You want to check the shear stud connectors that are connecting the deck to the assumed fracture girder to have sufficient tension capacity to develop plastic beam mechanism in the bridge deck after the assumed fracture event. You can design the shear connectors and the shear connectors on all the support diaphragms for combined shear and axial force according to the provisions of Article 6.16. Or if you choose, you can use the analysis presented in the research, the 5498 research. Just a little bit about detailing. You would detail the shear connectors to extend above the bottom mat of deck reinforcement. And then the top flange lateral bracing can be considered part of the resisting section for St. Venant torsional shears in addition to the concrete deck. And the contributions of the deck and the top lateral bracing are additive. So one of the most accurate ways to assess system redundancy of complex systems like twin tub girder systems is through finite element modeling. But such models, you know, they require a substantial amount of time to develop and analyze. And so there's two different ways that you can, or there's two different types of analysis that can be used to evaluate extreme event 3, and that's an approximate structural analysis that it was developed from the research, 5498, or a refined structural analysis. And so I'm just going to touch very briefly on these two. So a little bit about the approximate structural analysis. The entire self-weight of the span under consideration and the entire live load is assumed to be carried by the intact girder after the assumed fracture event. So it's very conservative. And you can use this method if your spans don't exceed 250 feet, if your supports are skewed no more than 20 degrees, you have a horizontal curvature greater than 700 feet, and then, of course, if the engineer ascertains that the use of the approximate analysis is adequate. So to use the simplified method, the bridge must satisfy 3 conditions. The first is the intact girder has to have adequate shear moment capacity. The deck has to have adequate shear capacity, and the shear studs have to have adequate tension capacity. And so if your bridge satisfies the first 2, but doesn't satisfy number 3, then a more refined analysis can be used to evaluate the ability of the deck to transmit the load to the intact girder without the shear studs connecting the deck to the fractured girder. So the TechStat Design Guide in Appendix C has a step-by-step procedure that outlines a simplified procedure. And I'm not going to go over all of this. I just kind of wanted to give the viewers out there a little snapshot of what is available. And I've highlighted the step 1 and step 2. You know, step 1 is design the bridge as you normally would. Step 2, design the bridge for member failure. The guide is about 17 pages in all, the Appendix C guide. And so I definitely encourage you, if you're interested, to take a look at that, and I'll give you the web link in a minute for that. So here's just some more pages from the guide. This is checking bending and shear capacity of the concrete deck. Here's another 2 pages, just skipping ahead. And this is checking the behavior of the shear studs. And so as you can also see, there's graphics that'll kind of help tell the story and help you to visualize exactly what the steps involve. So next, a little bit about the option for refined structural analysis. This accounts for the capacity of the intact girder as well as portions of that fractured girder that can still provide some structural resistance. And that was seen in the research. So that is definitely what is happening. The load distribution between the intact girder and the fractured girder can be realistically modeled this way. So for the refined structural analysis, it's modeled with that approach from 5498, the research. You would use nonlinear material properties. The girders would be modeled as shell elements. The deck is modeled as a solid element, and the deck reinforcing would be modeled as a 2-node truss element. So if you'd like more information about this, we have a policy manual, which is our bridge design manual. In Chapter 3, Section 17 is a twin tub policy. And then along with that, we also have a guide, and the guide is more commentary that supports our policy manual. And so those are the links, and those should take you right to the manual and the design guide. So moving on to FHWA approval and exactly kind of what that took as far as the Texas perspective. So that 2012 memo allowed owners like Texas to demonstrate that a structure had adequate redundancy, and be classified as system redundant. But under that memo, owners must submit each bridge for approval. So if you started going through your inventory and you needed to, have them deemed system redundant, you would need to submit each one. And that's still the policy now. But TxDOT's goal was to be automatically approved by FHWA if the bridge was designed using our TxDOT SRM methodology for twin tub girder bridges. So we decided to tackle the twin tub girder bridges because it's a bridge found in Texas. And so that was our goal, and that was the whole reasoning behind this. And so then those bridges could be SRM, they wouldn't be fracture critical, and they wouldn't require that 2-year hands-on inspection. So here's a little timeline of our FHWA approval process. So in May of 2018, we submitted our TxDOT Bridge Design Manual language for that SRM method for twin tubs to our local Texas FHWA bridge engineer. And then he submitted it to the FHWA headquarters in Washington, D.C. And then after that, there was a lot of back and forth email correspondence between TxDOT and FHWA headquarters. Within this time frame as well, we created that Appendix C that I just talked about. And so that was included, and that was sent to FHWA. And then in November 2019, TxDOT received approval for our method. So that was definitely exciting. So now I just want to touch on these two that I have these big arrows pointing to, the back and forth correspondence and then the guide, because as you can see, May 2018 to November 2019, that's a big gap. And so a lot happened actually between that time frame. So this next slide, you'll see a circle with the arrows that just keep going round and round and round. And so that's kind of how I pictured this process. FHWA would discuss our methodology. They would send questions and comments to TxDOT. We would respond with answers, and if we needed, we would revise our manual language or the guide to be more clear. And this occurred over several iterations, just a very open discussion between TxDOT and FHWA. And this process definitely made our manual better. It made our guidance more clear because we felt, if FHWA was asking questions, then there's going to be other engineers out there asking questions. So this process definitely made everything that we did better. It clarified things, and it also made us go back and say, okay, why is that? And then, we would find it, send it back. So it was very good, very positive experience, I would say. And then the next thing I just want to hit on is this bridge design guide. And I wanted to bring this up because, this really helped spell out our simplified method. It made it more clear. It provided a procedure that outlined each step. And I think this really helped FHWA see exactly what we were doing, because when we first submitted our process, we didn't have this. And then by giving them this and having actual equations, actual pictures, this really helped. And this actually was submitted in the fall of 2019. And as you saw, we got acceptance in December of 2019. So it was very, very good, or November of 2019. So I also want to say that the key to our success was collaboration, and extensive collaboration. It started with the research, we had the case studies, and then we had huge collaboration with Texas Steel Quality Council. We collaborated with AASHTO, T14, and some of the people that actually helped support that committee. And then, of course, FHWA was our huge collaboration with them. And so I definitely feel that that was the key to our success, was collaboration. So moving forward, our future twin tub spans will be designed using this TxDOT methodology. This is in our bridge design manual. This is required This is our policy now. And so that these bridges will be classified as SRM moving forward, all the new ones. We're currently developing in-house spreadsheet tools to allow for this simplified method. And so that's kind of the beauty of the simplified method, is you can create spreadsheets for this. We are also developing prototype refined models just to provide guidance for future redundancy evaluations. We have a future goal to also look at all of our existing twin tub girder spans and evaluate those for redundancy. And then we're also looking at a different type of component, steel component, which is the steel box straddle caps. Those are fracture critical. So we have a research project that's going on right now at the University of Texas looking at this component, bridge component. And so that is all I have for you. I'm going to turn it over to Andrew Smith, and he's going to talk about redundancy of steel twin tub girders in Wisconsin. Thank you.
Thank you, Jamie. Thanks to everyone out there listening, also to AISC and NSBA for the opportunity to present today. So here in Wisconsin, we've kind of approached things in reverse order, as you just heard from Jamie at Texas. We spent the past number of years evaluating our existing fracture critical tubs in the hopes of getting them reclassified as system redundant members. So that's what I'm going to talk to you about today. First, just an overview of what I'm going to talk about. Talk to you just kind of the makeup of our steel tubs in Wisconsin. Talk a little bit about the fracture critical inspection and the associated costs, user delay, and safety. And then the bulk of my presentation talking about the system redundant member evaluation and FHWA review. That whole process was broken up into a number of phases, so I'll talk about each one of those. And then lastly, moving forward, what we're looking to do for future designs. So some of you might be like me, where your personal and professional lives are blending a bit, and if you have kids, trying to find them things to keep occupied. So this is, I'll give you a quick geographical and cultural lesson on Wisconsin here from the eyes of an 8-year-old. So we're known for Packers, cheese, beer, and cows. Probably less known are that we do have steel tubs, and most of them are pretty new, less than 15 years old. And as you might expect, they're predominantly in our metropolitan areas like Milwaukee and Green Bay. And most of these had been brought into service as being fracture critical due to the definition of load path redundancy. Here's a picture of a couple of typical usages of tub girders. Generally, they're in our high-profile interchanges for our long flyover ramps. There are some exceptions to the rule. We have some over some geographical features like the Mississippi River, and then we also have some used kind of in a constricted area with tight radius. One thing I want to point out that's common to our designs of the tubs here in Wisconsin are these external diaphragms. Now, these are full depth, solid plate steel, and they're composite with the deck and generally located about a third span. These are, since they're obviously a composite with a deck, these are permanent. I know sometimes there's a tendency to take these out maybe for aesthetic reasons, but these are left in place here in Wisconsin. So fracture critical inspection, if any of you listening are familiar with it, you'll know that it can be costly. There's user delay and there's issues of safety. Because of the nature of fracture critical inspections being hands-on, it costs a fair amount, and then there's also traffic control, puts the traveling public at risk, puts our inspectors at risk, and so it's if there's a way that we can avoid doing it or lessen doing it, that's something we definitely want to look into. Just to talk a little bit about the resources required for doing a fracture critical inspection. Generally, for a bridge, you're looking at 10 to 24 hours, spread over a few days and nights. Certainly, this will depend on the size of the structure and how many people we have available. You have to have special access equipment. We call them sweeper trucks to give access to the underside of the girders. If we're running 2 of them, it's at least 4 operators and could be up to 6 inspectors. And then on top of that, we're talking about county staff doing traffic control, law enforcement. So it's quite a big thing to get these done. Let's see here. So cost. So every 2 years, we found that fracture critical inspection is required every biennium, so that's every 2 years, somewhere around $36,000 to $66,000 per bridge, kind of depending on if we have our own staff able to do it or if we have consultants hired out. But we're looking at roughly $1 million every 2 years to complete these inspections for roughly about 17 bridges that I'm talking about today. And that does include traffic control cost. Here's a picture of that snooper truck I was talking about with the inspectors in the bucket underneath the bridge. Note the lane closures in both directions of traffic. So for the safety of the inspectors, we close the lane where they're inspecting, and then obviously we have to shift traffic over into the other lane so that they can continue on with their inspections. So it can be a logistical challenge at times. As I mentioned, a lot of the tubs are in metropolitan areas, so daytime closures can be a bit unpractical, unless of course you're dealing with a pandemic. Maybe traffic's a little lighter. But generally inspecting at night, arguably I think the quality can go down a bit when you're working just with headlamps in this kind of situation. And then not to mention sometimes, getting traffic control is challenging enough, but then if you have to work with perhaps a railroad, some other entity to get below the girders offers another layer of challenges to inspection. So Dai and Jamie touched on this already, so I'm going to try to be brief. Basically, in 2012, this idea of an SRM came about, which a member that's fracture critical because it wasn't considered load path redundant could be considered redundant from a system redundancy standpoint if you could show that through refined analysis. So as you probably assume that I'm leading into, what does it get you? Well, it gets relief from that fracture critical inspection, from that hands-on inspection. Now, you still have to follow a fracture control plan when they're being fabricated, but the in-service inspection becomes much easier in the life of the structure. So how do you go about it? As of 2012, when the memo came out, it had mentioned that there's not really anything that had been codified in terms of guidance, how you're supposed to do this analysis. Since then, one important project was NCHRP Project 1287A. That was conducted by Dr. Connor at Purdue University, which ultimately culminated in NCHRP Report 883, which is fracture critical system analysis for steel bridges. That then fed into, later on, the guide specification, the Astro Guide spec for analysis and identification of fracture critical members and system redundant members. It came out in 2018. So these are 2 really important documents if you're looking for guidance on how you might go about setting up an analysis. And then lastly, the memo just talked about that whatever it is you're doing and proposing, that needs to be submitted through FHWA to get approval. So the next few slides, I'll talk about the evaluation that went into steel tubs in Wisconsin here. I want to note that NCHRP Report 883 talked about redundancy as it applied to multiple structure types. So today, this is kind of an example of how that methodology that was developed was applied to a specific type of structure, namely the twin tub girders. So that is the basis for the evaluation that was done on WSDOT. And we worked with, again, Dr. Connor at the Esprate Center at Purdue to do the evaluations, mainly for his involvement in the NCHRP project, and because this method relies heavily on a nonlinear detailed 3D finite element modeling, which is not generally in the toolbox of DOTs. And then just noting that, the efforts of that analysis were modeling was benchmarked to that full-scale testing at the University of Texas, Austin that Jamie had mentioned earlier. So I'll go over kind of the modeling. As you can see, it's a pretty detailed model. Shell elements were used for the deck. The reinforcement was part of those shell sections, kind of as like a layered shell. The parapets were included as solid elements. And then internal and lateral bracing were Timoshenko beam elements with connector elements that represented kind of the stiffness of that connection. And then also the shear studs were modeled as connector elements. And those properties were based on parametric study and calibration to full-scale testing. So once you got the model set up, obviously we're looking to load the bridge somehow. So as part of 883, two loading combinations were developed, a redundancy 1 and a redundancy 2. So redundancy 1 was intended to describe the loading condition at the instant of fracture. And if you look at that top equation, you see there's a dynamic amplification factor in there. For the tubs that Purdue evaluated, this was generally around 20%, a little less than that, of the static load. So 0.2 was used here. And then if you note the live load factor leading into that is 0.85. So you might consider that somewhat analogous to like an extreme load condition where you're assuming the event is occurring under normal traffic conditions, hence the less than 1 factor there. And so then under normal traffic conditions, the loading would be per the striped lanes on the bridge. So then redundancy 2 is describing the loading that would occur after the fracture happened, but before it was detected. And so with that, you see the load factors go up, approaching more of like an operating level, and then you'd be considering all the design lanes being loaded. And that's generally what controlled the evaluation, as we found. So then once you load the bridge, it becomes necessary to determine where exactly is the girder going to be fractured. So the FHWA memo from 2012, really the only explicit assumption dictated was that you had to assume one of the two girders fractured completely. And so that's what was done. And then multiple analyses indicated that where that critical fracture was in the end span, the girder that had the longest length if it was on a curve, so the outside girder, and then just before the first exterior diaphragm or near midspan, one of those two locations generally controlled. So once you have that all set up, you have to set up the criteria for which one would determine, yes, it's redundant, or no, it's not. And so we had a number of serviceability checks. I didn't put them on here, but such things as like the bearing, obviously, the girder can't slide off the bearing, that kind of things. But what you see here is more like strength requirements. So the average strain had to be less than the minimum of 5 times the yield strain, or 0.01. And the goal of this was just to limit redistribution of forces in the faulted state. Max strain had to be less than 0.05. And this is kind of conservatively selected. If you look at the typical stress strain diagrams of typical bridge steel, FHWA 0.05 is still on the ascending curve, so there's some extra load carrying in there, if you will. And then obviously we're not interested in anything buckling, right? So the compressive stress needs to be less than the buckling stress. And this, just as kind of an FYI, in the modeling that was done, because the finite element was so refined, this wasn't an explicit check because the model captured buckling modes. And then 15% reserve margin. So basically, the loading would be ran up an extra 15% just to verify that, like, we weren't right at the cusp of failure. So that helped build in some conservancy to this criteria. And then lastly, the strain in concrete set at 0.003. This wasn't necessarily a hard and fast limit, generally geared toward the deck itself, such that you weren't concerned with loss of strength in the structure from too much concrete crushing. So just insignificant crushing was allowed. We actually didn't see it very often in any of the bridges that were evaluated, some occurring in the parapets. So that was just kind of all the evaluation process that went into looking at the steel tubs in Wisconsin. So now I just want to talk about kind of the timeline of going through that process. And as I mentioned, we approached it originally looking at all the existing structures. And then currently, we're looking at how can this be applied for future designs. So we started back in March of 2015. And we started gathering information on all our tubs. We reached out to Dr. Connor and started putting this together. And so in 2016, we put together this pilot phase report. We picked a structure, we ran it through this proposed evaluation criteria and submitted it to FHWA. So these circular arrows kind of represent this back and forth that happened in terms of comments and then providing answers to that and coming on to an agreement on how to go about it. And then in May of 2016, the pilot bridge was approved to be an SRM. So then that led into more structures being submitted once we had the process down. And that happened in 2018. We had a little break, if you will, in between. We started looking at how can we evaluate structures without relying on advanced finite element methods to evaluate these structures. So that's what the light blue is there. And then lastly, in terms of the existing structures, we had a phase 2, which looked at some structures that had some unique characteristics. We weren't super confident that all of them would pass and be reclassified, but that's what that is. So I'll go through each one of those. Just talking about that pilot analysis. So bridge in Milwaukee, this one was kind of a tight radius bridge, 2 spans. It was funded by NSBA and WISTOP. And as I mentioned, this one was analyzed based on what was being developed as part of NCHRP Project 1287A. Report 883 hadn't come out yet, but much of that information was already in the works. So through that, through those criteria that were being developed, that structure was determined to be redundant. We submitted it to FHWA, and it was approved for reclassification in 2016. So just to, kind of detail what it was we submitted to FHWA during this phase, everything I talked about prior in terms of the modeling assumptions, how we would load the bridge, where it was fractured, the criteria that we were benchmarking to say whether or not it was redundant or not, all that was detailed in a report, and then obviously the results of that structure going through that evaluation process. And just to speak to it, FHWA is very supportive of this type of evaluation, looking at getting these structures off the fracture critical list. If it's deemed reasonable, they provided quality review and feedback in a timely manner, so it was a positive experience working with them to get this structure reclassified. So as I mentioned, once we kind of worked out all the details of what the evaluation would look like, we entered phase 1, and we had 12 extra bridges that we were having Purdue analyze. And so these bridges kind of represented a wide spectrum of geometry and layouts. We had some that were tight radius, and then we also had some really long multi-unit overpass type structures. The cross-section shown on the bottom there isn't an actual structure, but just kind of represents the ranges of structures that we were looking at. They all could either carry 2 to 3 design lanes with girder space somewhere between 16 and 25 feet. Kind of interesting, there's some different design approaches to tubs. Sometimes they end up getting a little wider, slender members. Necessitates usually like a bottom flange stiffener over the pier, or in some cases the designer prefers to go with something more slender, so the members are a little more robust, sometimes relying on higher grades of steel. But all to say that given the diverseness of the bridges that were submitted, all of them were determined to be redundant and were reclassified in 2018. So this was a little PR blurb that we submitted after successfully having 13 of these reclassified. Really just trying to, buck this idea that, fracture critical bridges are inherently unsafe. When in fact, what we've done here is presented information that builds confidence that these structures are safe and have plenty of capacity, even given one of the girders fracturing. And in doing so, we've saved taxpayers money, and we've also improved the safety of the traveling public and inspectors. And those resources can now be used elsewhere. So this was kind of a little break we took from the refined analysis aspect of it, and we took a bridge and we started developing sort of a sandbox, right, of everything that had been evaluated up to this point, kind of defined the limits, such that, if we had a bridge that fit within those limits, it would also achieve SRM classification without the need for FEA. And so that's what we've done here. Some of the criteria that, we worked off of had to be designed LRFD, had to be a multi-span continuous structure. It needed to have those full depth intermediate and external diaphragms, had to be composite, and then of course putting on some section and system limitations in terms of like span length, span ratios, the radius, sectional properties. So the bridge we did this for was in Green Bay. This bridge did not get evaluated using finite element analysis that was covered in detail earlier, but it had some sister structures that were. So we developed, like I said, these criteria to show that yes, this bridge fits within those limits of the other structures that had been shown to be redundant. And so we submitted that to FHWA. They approved it. They like the concept of developing something that doesn't rely on finite element, like a statewide policy that we could use to automatically classify structures as system redundant. But at this point, it still remains a case-by-case evaluation. So our goal later is to get to a point where automatically these bridges will become SRMs. So phase 2, this was the last phase as we evaluated our existing structures. As I mentioned, all these bridges had some kind of unique characteristic that was different than the rest we had looked at. At this point, the Astro Guide spec had been released. So the result was that of the 7 bridges we looked at, 3 of them were able to be reclassified as SRMs, and the remaining are still fracture critical. And I point that out in the following slides. I'll show kind of which ones made it, which ones didn't, and really just to point out kind of the obvious that analysis isn't going to guarantee that your structure will be considered system redundant, but it should help give you an idea of what kind of success you might find if you were to look at your existing structures, or identify ways that through retrofitting that you might be able to achieve that. So this first one, this is a fairly modern structure. What was unique about this one was the existence of that integral crosshead, just to provide clearance for the roadway below there. We had to shorten up the pier. So in addition to doing the evaluation where you cut one of the main longitudinal girders, we also cut that diaphragm. And what I think saved us, ultimately this was past the evaluation, was that top flange and that crosshead, there were actually two of them bolted together. So the assumption was that the web and one of those flanges, the one welded to the web, fractured, where that top one continued to transfer load. So this one successfully was reclassified as an SRM. These two structures are sister structures. They were put through the evaluation method and also passed. I want to point out what's unique about these structures is that they don't have those full depth diaphragms, and if you note in this cross section, they're not composite with deck. So it's just to show that the existence of a full depth diaphragm that's composite helps considerably, but it isn't like a game changer. It's not like something that you have to have in every case. So getting into some of the ones that didn't pass, the picture just kind of speaks to ominously that it just didn't work out well for us. This one actually was a straight tub girder. There were no shear studs over the piers, and then these cross frames, as you can see, are just kind of some wimpy angles. So this one, when we passed it through the evaluation method, didn't meet all the criteria and remains fracture critical, and that was due to bottom flange buckling over the pier. This one's also a fairly modern structure. This one is over the Mississippi River, and you'll note that there are no intermediate diaphragms in this structure. So this one also, when ran through the evaluation process, didn't pass. Also bottom flange buckling over the pier. This structure is unique in that you can see the end span being the critical span generally when you fracture it in the analysis is fairly long, and it's not balanced well with the adjacent span. So this one, when we had it analyzed, also didn't meet the criteria that was established due to local flange buckling. And then lastly, we have a single long span, single span structure in the state. This one did not have also solid diaphragms in the middle, and this one also didn't pass. So this one remains fracture critical. Now this one really had an issue with shear stud failure. So I want to kind of circle back to key features that we found from the evaluation process that occurred in these tubs. Just showing that analysis demonstrated the benefit of relatively stiff external diaphragms. And that's based on simply looking at, these structures passed and these didn't. And then in addition to that, Purdue did an analysis of kind of a representative bridge and evaluated with and without, and found that without them, you generally saw excessive shear stud failure. So next steps. So we successfully removed 17 of our existing structures from the fracture critical list. So that was a great benefit to us. Moving forward, we know kind of what it is that causes some issues in our structures, and so looking at possible retrofits to address some of those structures that were deemed not structurally redundant, sufficiently redundant, sorry. And then, like I said, one of our goals is to have a policy for new designs that would be automatically classified as SRMs. So talking a little bit, this was mentioned, Dai mentioned this a little bit earlier, Purdue has proposed a simplified approach for designing SRMs, which is intended to complement the AASHTO SRM guide spec that's out there. And it could be used for both new and existing designs, and it's subject to geometric limitations with some additional design details and checks. The key thing to this is that no FEA is required. So some of those geometric limitations, these bridges would go through a screening process, right? So certain checklist items, right? It has to be continuous and composite. There'd be limits on, parameters such as deck width, span length, skew, etc. And then one interesting function that they found through this analysis was that the dead load deflection was kind of a good indicator on whether or not the structure would pass the established criteria. So it's put some limit on dead load deflection in the unfaulted state, so that you would avoid classifying something that tended to be more flexible, which could result in significant inelastic behavior. And the nice thing is that these deflections, this dead load deflection, can come out of like typical engineering programs that we have, like MDX, CSI Bridge, something like that. Establishing certain design details, so there'd be requirements on shear studs, the layout, the height, specifying details for the external diaphragms. And then in addition to that, there'd be a couple of basic design checks. So the idea here is that if you hold the structure to some certain geometric limitations with some design details, you're going to isolate what the expected failure mode is based on all the evaluations that have occurred already. So some of the additional design checks that it would go through is just checking negative moment region near the flange transitions and establishing a minimum demand to capacity ratio. And then also in the positive moment region, having a minimum DC ratio to avoid plastification of the intact girder in the faulted state. So that's all I had. I'm going to pass it back to Dai just for some closing remarks.
Thank you, Angie. Okay, can you hear me? Because I think my earphone may have a little bit of volume.
Dai, we can hear you. We can hear you.
Okay, that's good. At the end of the webinar, I'll confirm again the full support from FHWA to encourage the proper use of SRM. We just had a FHWA internal discussion yesterday afternoon on this. Joey, Derek, and myself. Justin was in vacation, but was very informed. In doing the SRMs there, please follow this process. State DOTs and researchers may propose procedures for SRM determination, not limited to twin top girder bridges. We are now stressing more on the procedure acceptance than individual bridge approval. We try to go that direction. We've got good progress for twin tops. However, for any newly developed procedures for bridge types other than twin top bridges, we must proceed more cautiously. At the present, both the procedure and the analysis should be submitted to Federal Highway for acceptance and for approval. The third bullet point, the review acceptance process should go through FHWA division office to headquarters. Fourth bullet, a bridge owner may seek FHWA approval of using another bridge owner's procedure that had been accepted by FHWA, like Texas and Wisconsin already obtained here. also sent to FHWA division. All determined SRMs with their supporting documents should be recorded in the bridge files. I think that's basically is the reconfirm FHWA support, and we're willing to work with the states and with the with the steel industry there. Now I'm back to you, Nate.
All right. Thank you very much, Dai, and thank you also to Jamie and Andrew for that excellent presentation. So we're going to go ahead and move into a question and answer phase here shortly. We had a lot of good questions coming in from the audience that we'd like to get to. But first, we're going to do a few interactive polling questions that we are going to pose to the audience. And so we're going to do one for each part of this presentation. So the first one is as follows. This is a true or false statement. True or false, the only FHWA accepted procedure for SRM determination is to use full 3D nonlinear dynamic finite element analyses. Is that a true or a false statement? The only FHWA accepted procedure for SRM determination is to use full 3D nonlinear dynamic finite element analyses. Audience can select the answer they think is correct. All right, let's go and see what results came in, Dai. And it looks like 95% of the audience think that that's a false statement. Did they get that one right?
95% people are right. I don't need to explain anything this clear.
All right, that's good.
Very
All right,
clear.
let's see if the next ones are any more difficult. The next question. When designing for the extreme event of member failure using the text design methodology, which type of analysis assumes the intact girder carries all of the self-weight of the span and the entire live load? Is that A, the approximate structural analysis, B, the refined structural analysis, C, both A and B, or is that D, neither A nor B? All right. Well, let's go ahead and go to the results for that one. All right, Jamie, this was from your part of the presentation. It looks like about 2/3 of the audience thinks that the answer is A, approximate structural analysis. The second most popular answer was C, both A and B, at 22%. What were we looking for here?
The correct answer is A, approximate structural analysis.
All right. 2 for 2 so far, so let's go to the final one. What was the key feature highlighted in the system redundant bridges in Wisconsin? That A, 3 or more tub girders. The B, external full depth plate diaphragms. Or is it C, straight bridge? In the question here, what was the key feature highlighted in the system redundant bridges in Wisconsin? All right, let's go to the final poll results. And it looks like it's overwhelming, Andrew, that 96% think the answer is B. Did they get that one right?
That is correct, yep.
All right, good job, everyone. So let's go ahead and get to some Q&A. Have some good questions come in from the audience. Dai, I'm going to start with you. This is a question sort of related to your final message here. So the presentation today focused on twin tub bridges and SRM classification achievement. Is there any information available at this time through FHWA or elsewhere for other more common bridge types that might be good candidates? the question asker says, it is understood that each agency would need to do an analysis anyway, but some additional guidance might be useful.
Yes, at this moment, the Federal Highway has some limitation to give a specific guidance because of the executive order. But anyway, FHWA, as I said in the last slide, give full support of proper use of system redundant concept there, and is encouraged to provide, based on your started research and propose the procedure, and to more than twin top girder bridges there. And I've noticed that some comments is talking about how about the truss, and also you can say the straddle band, and you can say talking about tied arch or something, whichever way there. We look forward to the open to the new procedure. That is basically is our position there. We don't restrict how you do it, but we would like to see it, and we want to move cautiously. Hopefully,
right.
This answers the question.
Yes, thank you, Dai. Let's go back into. Let's just look at slide 55 for this next question, and this question's for Jamie. And the question is, do the intermediate steel diaphragms have to be full depth in TxDOT design processes?
Thank you, Nate. So the answer to that is the diaphragms should be as deep as practicable, but at a minimum, they should be at least 0.75 times the tub girder depth, and that's actually in our bridge design manual, so you can find that in there.
All right. Sticking with you in your part here, Jamie, let's go and look at slide 81. And that question is, how long do you expect it to take TxDOT to demonstrate to FHWA that all existing twin tub girder bridges in their inventory are SRN and do not require FC inspections?
Thanks. That's a good question. And first of all, kind of like Andrew said, just because we run analysis doesn't mean we'll be able to demonstrate that they're SRM. I'm sure there'll be some that'll still be FC. But we're currently working on a prototype for the refined analysis. So after we do this, we have to start looking at each bridge one by one. We've already documented all the twin tub bridges in the state with a spreadsheet, kind of outlining geometries and unique features for each bridge. And we'll most likely do this in phases and analyze a few bridges for system redundancy, and then send those bridges in a submittal package to FHWA for approval. And then if all goes well for those, kind of that pilot submittal, then we'll be able to reclassify those bridges and continue to evaluate bridges and just submit in phases. So as far as the timeline, it'll probably be a while. I can't exactly put a time on that. And I don't know if you saw Andrew's, it was several years that it took him to get it finished.
All right, thank you. Let's move to slide 112 for the next question. This is in Andrew's part of the presentation. So the question is, for these examples starting at slide 112 of bridges that you weren't able to qualify as SRMs, have you considered doing retrofits to make them SRMs? It appears that some simple things might be done to get them within that group of SRM.
Yep. So like I said, our focus right now is kind of establishing our criteria for design moving forward, but definitely coming back to some of these other bridges is something that's on our radar.
All right. here's a question also posed to your part here. I'm going to go actually back to slide 89. And this is where you're talking about the cost. So the question is in general, for these in-service structures with FCMs, have you figured out that there is a point at which the cost of performing analyses show that there are SRMs might actually outweigh this cost of doing the biannual inspections? And that's sort of a detailed question, so I'll just ask Andrew if that's something that you have any feel for.
Yeah, so I won't throw out specific figures, but it was definitely in our interest to have these evaluated. And the great thing is that it just keeps paying back, right? Every 2 years, that's a savings. And so it was definitely worth it for, let's see, we had 17 structures that went through this process. Actually, holding back, I think, like the one that we did, a parametric evaluation, like 16 structures or so. It was definitely worth it.
All right. Well, I think we're going to stop there as we're a little bit past the top of the hour here. So I just want to let people know out there, we did get a lot of questions. Unfortunately, we can't get to them all here in the live portion, but we did receive them, and we will, work to provide some responses there by email following this webinar. So thank you to everyone for your participation.